Hey, how's it going? Changed my title and my description up. I doubt it'll help the SEO, but who knows? We'll see. All right. We'll see. Nice. Yeah, sounds like a lot of fun. Okay, let's see, where were we here? So I did some work integrating GUI, pretty much got that done. So now we have a debug GUI here layer. So I can use the metrics. You can see the frame time. This is just the demo window, so it's just what comes with a default GUI integration. But we'll be able to build our own debug UI on top of it, so that will be useful for adjusting properties and whatnot. You can see you can also do like custom rendering and stuff. Let's see, examples, custom rendering. This is pretty cool. So I can pretty much just insert any kind of graphics you want over your game graphics. Very nice for debugging. Yep. Cool. Okay, so I think I need to have some memory management now with Vulkan. So I'm gonna go ahead and use this library called Vulkan Memory Allocator. Go to GitHub, Vulkan Memory Allocator. And just copy this GitHub, and then since we're using CMake, we can just go to where we're adding our dependencies, right here, and we can add another entry for it. Call this Vulkan Memory Allocator. And we'll decide which version we want to use. So I'll just use the latest version. You can click here and then you can see on the tag section all the versions they have released. CMake recommends that you use the actual SHA hash instead of just the tag ID, since it's a little bit more secure. You can actually check, make sure you're getting the right thing from the right source. So we'll actually click on this here and we will go to the recent commits and we will copy the latest SHA hash for that particular commit. And we will paste it into the git tag entry. And this is version 3.1.0. And then we need to make it available right here. So now it's going to download that library and put it into our directories. So if I go into my directories, you'll see that library is now here and the GitHub source has been downloaded. So now all we need to do to link against it is add a entry into our target link libraries for Vulkan Memory Allocator. Just like that. Okay. now we should be able to go in and use this library in our code base. So if I try to include a file, sometimes the library name is different than what I specified. So let's see, VMA. That's Vulkan memory allocator. See what the include structure is. It's VM mem alloc is what it is. Or VK mem alloc, I mean. All right, so now we're able to include it. And now actually, we're done at header. Let's include it up here. And then we'll make a function here. We'll call it create allocator. And it'll take in an instance and probably a device too. We'll put that under create logical device. And then I believe, let's look at the documentation here. VMA documentation. Let's see. Vulkan memory allocator. Let's see. Initialization. To initialize, we need to create a VMA allocator create info. Okay, so I'll just keep this here up on the side. So we need a VMA allocator create info. We'll just call that alloc create. And unlike the regular Vulkan library, we don't need a structure type field in there. We can just do that to initialize it. Let's see, so we need to pass in a flags for this. What flags do we want? I don't think we want any flags right now. We will in the future, but I think right now we're good. So yeah, we don't need dedicated allocations yet. We will use this memory budget thing, but not yet. So we can just leave that as 0 for now. And then we need to tell it the API version that we're using. And I believe we just have that as a constant up here for the API version. Yeah, VK API version 1.2. Let's actually move that into a macro. So I'll just define VK version, and I'll just define it as that. Or we'll say, we'll make it a little bit more descriptive, and we'll give it a prefix there. Yeah, and then we can just use that wherever we need the VK version. And so down here, we'll give it that as well. Okay, now we also need the physical device for the allocator. So maybe we need that instead. Oh, well, we need all three actually. So we need the physical device, we need the instance, and we need the logical device. So we will pass all three of these in to this function here. Yeah, and we can do that just like this. Instance, and then the physical device. And the logical device. Okay. And then we also, so it says there's a thing for passing in Vulkan functions. Can be null. So we don't need to pass those in because we're just using the ones that are provided to us from the Vulkan library. So we don't need to do anything there. And I think that is pretty much everything we need to initialize here, because everything else can be kind of left defaults, right? Yeah, so I don't need that. And then there's some more customizability here, like the heap size limit, and it kind of gives you descriptions here, but we don't really need any more specific functionality for our use case just yet. So we can now use this and pump this into the creation function, but of course we're working with handles, so we need the VMA allocator handle that gets returned. But this is actually going to be returned as a reference passed into the function here. So we're going to do VMA allocation, or allocator, sorry, allocator reference out allocator. That's the fourth parameter to this function. Yep. And it's going to be VMA create allocator. And we're going to pass in that creation struct, and then we're also going to give it the output here. And then the return value of this function is just going to be whether this is with a VK success, because then we know it worked. So that's going to be for creating the allocator, but we also need a way to destroy the allocator when we're done with the program, and we'll do that here. To destroy the allocator, you really just need to give it the allocator. So the allocator, that. I'm probably going to have to restart Visual Studio because it's giving me random squigglies that don't make sense. Let's do that. And then we're going to do VMA destroy allocator here. And pretty simple right there. Just a wrapper, really. Let's go ahead and restart Visual Studio. Okay. So let's go back into our main file and create graphics context. So right under where we're creating the logical device, we're going to create the allocator. Right. Create allocator, and we just pass in the instance, the physical device, and the logical device. And then we need to add a new field in here for the allocator. So we'll do VMA allocator, and we'll call this mallocator. So as you can see, the convention for member fields here I've established is adding a prefix m field. One of the nice things about doing that is, say you have a function here, not that we have it right now, but say you have a function called set render pass, right? And say you passed in a render pass like this. Well, typically, you would call it something like render pass, right? And well, if we didn't have that n prefix and we just called it render pass, well, our options really would only be this render pass equals render pass, right? Otherwise, we would have sort of an ambiguity if we just did that, right? And that's not good. There's other ways of doing this, like adding an underscore, but I just don't like the way that looks aesthetically, honestly. I'd much rather just have the n prefix. I think it looks a lot better. So that's why that was chosen. So I just think that it's a good balance between code aesthetics and readability. So yeah, now we just need to pass in that allocator right here. So let's pass the allocator, and then we can give a good logging message right here. Failed to create Vulkan allocator. Yep. All right, and let's test, make sure our new allocator is set up correctly. And we got a build failure. Let's see what happened here. Create allocator must return a value. Okay, yep, we have to return. We've got our return statement right there. Undefined symbols. Okay, so this right here is a little bit more interesting. It's saying that these library functions are not defined. So unresolved external symbol, VMA create allocator, referenced in function create allocator. Well, we are linking to the library, so that is a little strange. So let's see what's going on here. So we have private Vulkan memory allocator. So this means that it's probably not actually linking to it properly. So let's go into VMA and let's kind of dissect the CMake target a little bit to see what's going on here, because maybe it's adding some sort of target in a strange way. So let's see if it's adding a library. Vulkan memory allocator is an interface library. Okay, so that means that that one is not going to actually compile, interestingly enough. So I wonder if there's some sort of define that we need to use to actually get it to define these resources. or these functions, that's probably the case. So if we go to vk minmalloc, maybe there's an if defined somewhere. VMA implementation. Define VMA implementation. Is that defined as 1? Let's see, VMA create allocator. VMA public interface. Okay, let's see what's going on. So if we go and look at where that function takes us, okay, so this is just the prototype declaration. So this is clearly not actually creating the implementation, but we need the implementation to be created. So that's going to be this VMA public interface right here. So if not defined, VMA public interface. I think we do. Okay, so VMA static Vulkan functions, dynamic Vulkan functions. Public interface. Let's go ahead and grep for this. Let's grep for that. And okay, so I think add library. Okay, so probably just need to define VMA public interface. But probably should define that in the header file. And then in here, I'll just include that. Okay, I don't know how I didn't say that. VMA implementation is what we need. We should be good there. Yeah, I was gonna say you don't usually define those ones. Okay, that should work. Cool. All right, and our allocator is created successfully. And continue, and yep, everything still works. Still got our GUI. I also implemented resizing, so you can resize dynamically and everything. Though for some reason the AMD driver is very slow to resize. I already profiled this. For example, if you drag around and resize this window a lot in the Visual Studio solution, and then you break all, you'll see here, if I select the range where I was resizing, you can see the CPU spike, and then if I open the details here, expand by call tree and look at the hot path, you go all the way down and you look that your hot path is 80% VK create swap chain KHR. The AMD driver is taking ridiculously long here. I don't know why, but I looked it up on Reddit and that seems to be the case as well. And if you also go and look at the built-in VK cube app in the Vulkan SDK, if I open that real quick, it also has the same behavior. So it's very strange. For example, if I open this is the app that literally ships with the Vulkan SDK. Resizing the swap chain, every frame is so freaking slow. Why is it this slow? I don't know. It's not this slow in the NVIDIA driver. So I might need to see if there's an updated driver out there for that, because it should not take this long. But it's okay, we can deal with that. All right. So we have our allocator. Now that we have our allocator, we can start doing some resource allocation, like creating buffers and images. And really all VMA allocator is doing is it's managing the GPU heaps for us, so we don't have to allocate our own blocks of GPU VRAM, right? But we still have to sub-allocate within our buffers, right? So that just takes one layer of complexity out of the equation. You can manage your own GPU memory. It's not that crazy hard. I mean, it's just like managing any other memory. But you'd have to create your own allocator, either using something like a buddy allocator or pool-based or linear allocator. There's all kinds of allocation techniques and algorithms out there that have their own trade-offs. And so for now, we're just going to, because we're really going to have to create our own allocator anyways when it comes to managing the sub resources within the buffer, right? So we're not going to bother with creating 2 layers of complexity there. So yeah, all right, let's see. Let's go ahead and just submit that real quick. Add VMA. I'll just type it out. Vulkan memory allocator library create allocator and commit that. Cool. And then one thing I did forget to do is we need to dispose of it at the end of our application here. So we'll destroy graphics context. We are going to destroy the allocator right here as well. Yep, allocator. Do that right before we destroy those resources. Okay. So let's take a look at creating buffers. Because you need buffers for all kinds of things. You need them for vertex buffers, you need them for index buffers, indirect buffers, all kinds of buffers, right? You need them. So let's scroll down. I did split out our files here a little bit, so we might do another cleanup pass real quick. So we have this file here that sort of manages like swap chain and surfaces, right? Maybe not surface. Does it create surface? It does not. Okay, so let's see. Create surface. We're going to move that into our swap chain code as well, because surfaces and swap chains pretty much go hand in hand, right? So let's move our surface code and swap chain code into the same file. And if you're not sort of familiar with Vulkan, you know, like a surface is it's the abstraction over the windowing system, right? So like a surface might abstract over Win32 windows. It'll abstract over, you know, X window on Linux, or you know, layers on Mac, that kind of thing. That's what a surface does, is it just abstracts over the operating system windowing layer. And the swap chain is really creating resources to render into that window resource, right? Because in a swap chain you can have multiple things. Yeah, Wayland. You know, there's different implementations out there. I know that's the most up-to-date one, but that's essentially what the surface abstraction is. In Vulkan, it lets you go into it. So it's very platform specific, and so that's why we let GLFW sort of manage that resource there for us. Yeah, so let's go ahead and take that in our refactoring and let's just move that into the swap chains. These are pretty much hand in hand here. And let's also move the include that we need up here for GLFW. Move that right here. And we actually need that in the header file as well. Okay, so we move that over here. Okay, and we don't need that included. So let's also create another thing here. So there's a bunch of Vulkan sort of functions just added in here. This is graphics.h. There's also graphics.cpp. I'd like to mess around with Linux from scratch. It would be interesting to do that and looking at making a custom desktop environment. Yeah, that would be really cool, a learning experience for sure. Those sort of low-level projects. So we have our a lot of core functionality in this graphics.h file here, right? So we initialize our Vulkan instance, we pick our physical device that we want to render to, create our logical device for that physical device, create our allocator, destroy our allocator. This is all pretty core functionality, but then we start getting into things like command pools, command buffers. I'm going to move that into a separate file. Let's go ahead and do that right now. So this is going to be, and we're going to call that graphics command, right? Because these are all sort of command related functions, right? So we're going to make a graphics command.cpp and graphics command.h here. And we're going to stick to our namespace conventions vortex. The thing I like about having this refactoring tool is that if I wanted to rename this namespace, it's very simple using this tool because all I have to do is hover over it and use my shortcut and I can rename the whole namespace instantly. So this is really just a code name right now. Okay, so we have that. We need our pragma once. And then let's start moving our stuff over here. So I think I want the command pool management to be moved And then all of these functions that have anything to do with command buffers, I'll put that under. And then let's include the Vulkan header in here, since that's Vulkan. And then let's also include our immediate helper function that we wrote last stream in here. And we need our functional header, functional. And pipeline barrier also comes into here. And we also need the struct to declare pipeline barrier information. And we need vector as well. And I think that's everything that we want to move out of here. Yeah, that's everything relating to commands. So the nice thing about using a strongly typed language like C++ is we can do the break it and fix it technique, where we purposefully create compiler errors and we go through each compiler error and fix it. Something you can't do with JavaScript or Python as easily. That's why strongly typed languages, in my opinion, will always be the best languages. Let's go ahead and include graphics. Allocate command buffer. Yeah, we need to borrow that for create frames, so there's nothing wrong with including that there. And we'll take immediate and pipeline barrier out of here. We also need to include graphics.h. To get these VK macros that we defined. Okay, and I think that, yeah, that looks like it's everything that we want to move. Okay, what is this? C error. Okay, we gotta also take an IO stream. Fun fact, AMD actually wrote this library, Vulkan Memory Allocator. I just remembered that because looking at the macro, AMD is prefixed into it. So this is actually an AMD library, but it works everywhere. A lot of people use it too. Cannot include vkmem_alloc. What a strange error. Where's that originating from? I forgot to turn my warnings as errors on. I need to do that after I fix this error. Or, yeah. I like keeping warnings as errors on because it helps you find bugs a little bit earlier. Well, that's the weirdest thing ever. It just fixed itself. Don't you just love that? I don't know why it fixed itself, but it fixed itself. Okay. This probably was something was out of date or whatnot. So, yeah, not sure what happened there. Okay. And then I want to commit this refactor commands related functionality into separate graphics command.header/.cpp. And submit and push. Okay. So like I was saying, I want to turn warnings as errors on, and we need to have a switch on which compiler we're using because this is compiler specific. So in CMake to do that, we do if and then MSVC. And since we're only doing Windows development right now, we do this. If you're using a different compiler, like maybe you're using GCC, you know, there's switches for how to do that, right? Like you would check what compiler you're using right here, right? And then you could add that compiler specific compiler flags to the target, right? So because we're just on MSVC right now, we're going to do target compile options, right? And we're going to make these private, which means that any project that depends on our project right here is not going to inherit these. We don't want another project to inherit these because this can be annoying for other projects. So we're going to give it warning level 3, and then we're going to also give it warning level X, which just means higher level warnings, and treat those warnings as errors because we don't like it. Warnings are bad. And we're going to save that. And I'm going to compile it. I'm probably going to get some errors because of this now. Yep, get some errors, and you can see here everything. It says, oh, hey, this is a warning, but actually the following warning is treated as an error, right? And why is this? It's because we're using this standard size right here, which returns a size t, but we're actually trying to assign it to a uint32. And so that's okay, right? There's an implicit conversion, but generally speaking, you want to be explicit about these kind of things and add like a static cast right here, right? The old style C cast would be just doing in parentheses uint32, just like this, right? But you'll notice that I'll get the screen squiggly with clang tidy. It'll say, hey, why are you doing that? This is C style cast instead of a C++ cast. You actually want to be using static cast. And the reason for that is mostly because with the C-style cast, you don't know what kind of cast you're getting. C++ has different casts, right? You have static cast, dynamic cast, interpret cast, const cast, right? So you want to be explicit about the kind of casting you're using. Yeah, let's see. The other error is probably similar. So we're assigning a bool to an int, right? And this is just because GLFW, it's like a C-based library, and so it's kind of using this int as a bool, and we're sending it directly to a bool. So one way we can get around that is just casting this to a bool as well, doing the same exact thing, right? And that'll work just fine. And we get another error. Conversion from size t to uint32, so we have another parameter over here, it's size t, but it really needs to be a uint32. So we'll go ahead and do the C style cast right here, or the C++ style cast right here. And then we're assigning a optional size t to a uint32, and guess what? It's the same exact fix. And it works. All of our warnings are cleared up, so we won't get warning spam when we build. That's another nice thing about this. And generally speaking, when you're building open source software, I highly recommend that you use warnings as errors always. Because when somebody takes your software and they pull it down and they build it and they get like a crap ton of warnings, it's not a good look, right? So it's especially important if you have something on GitHub. So let's go ahead and push that now. Enable warnings as errors and fix warnings. Okay, so we've done that. We split this out. Nice little refactor here. Now we want to actually create some resources. So let's make another file here. Let's call it graphics resource.h and .cpp. And let's make sure our CMake, because for some reason, when you add files on Visual Studio with the CMake integration, Visual Studio, if you're watching, which I know you're not, because I only have one viewer, please fix this. Every time I add a file in CMake, it adds it to multiple targets. It doesn't make sense. Why is it adding it to multiple targets? It should only add it to one target. At the very least, only add it to one target. So I'm deleting it from this target. Okay, now we can include a new file here. Let's do once, namespace. And there are a few other things that I do want to bring into here, into this new resource file, namely descriptor pools. Yeah, so descriptor pools can come into here. Let's do Vulkan.h. Yeah. So, and if you don't remember from last stream, a descriptor pool is just a way of telling Vulkan. It's essentially a pool of memory that the driver is going to allocate your shader resource bindings from. And if you're coming from OpenGL, that might sound really confusing, and that's because it is. That's the one part of Vulkan that I think a lot of people are very like. That's the one part of Vulkan that I think they're kind of working on changing, right? Because you have this concept of a descriptor pool that you have to like sort of allocate, and you have to tell up front, like these are essentially the max resources I want for each type, right? And you can see when we're creating our descriptor pool over here, we're sort of telling it, hey, we want all of these different types of resources, and here's the maximum amount. And I'm not sure if that's telling the driver, hey, driver, pre-allocate this amount for this type of resource, for each type of resource, right? Or it's essentially just telling the driver, hey, this is how much I'm going to use for this descriptor pool. And then from that descriptor pool, you can allocate descriptor sets. And the descriptor sets are what you actually bind to the shader, right? And descriptor sets contain the actual data, right? So it might be your buffer with data that you're sending to the shader, might be a list of textures, you know, it's really like, those are the two main types of resources, is like a buffer and an image, but there's different types of images and different types of buffers, if that makes sense, right? Like you could have a uniform buffer. You could have a shader storage buffer. You could have a texel buffer, but a texel buffer can actually be interpreted as an image in the shader, right? And so we'll get to all of those concepts as we go on. But for now, just know that the descriptor pool system is a little bit confusing in Vulkan, and I hope that they're one day going to simplify that. It seems like they're, with Vulkan 1.3, definitely moved in the right direction with some of their dynamic state stuff, which I think we're going to be using here. Standard size, X utility, I do not want that. What is that? What header is that in? X utility, I've never heard of that header. But standard size is defined in a ton of headers. So yeah, I think we can literally just include the array. I think it's the array, maybe. I'm just going to, so weird. Yeah, I guess it is just an X utility. I didn't know that that was actually, is that a core header file? That's kind of strange. I'm not going to include XUtility because that doesn't sound very cross-platform to me. That's kind of sketchy. I'm just going to include array because that has it in there. I have no idea why that's not just declared in like a standard file. It seems to be in some sort of MSVC utility file, so it's kind of sketchy to include that directly because that maybe wouldn't compile on like Linux or Mac. All right, so we got that. Create descriptor, cool, we moved that over. Okay, so now we want our create a buffer, right? Yeah. So we want to be able to create a buffer. Create buffer. And if you've used OpenGL, you know there's a bunch of different types of buffers, right? You have index buffers, vertex buffers, indirect buffers, all these kinds of buffers that can do different things. In Vulkan, the concept of a buffer is entirely generic in the sense that you can create a buffer and it can do whatever you want, right? You just have to tell it what it can do, right? And then you manage that memory however you want, right? You give it a stride, you give it an offset, and then you give it the range that sort of maps to this particular type of buffer. And so you can do that bulk. So basically, if you wanted to have everything in your program in one buffer, you could do that, and that could all be on the GPU, right? So obviously for a buffer, we're going to need a size, right? Like every buffer needs a size. There's no real way to like resize a buffer without deleting it and reallocating it, right? So you're going to want to create a buffer with as much size as you sort of expect to be needing. You don't want to be constantly resizing buffers, right? So we're going to give it a size. So let's actually start from creating the VK buffer create info first. Buffer creates, just like this. Let's give it its type, buffer, or structure type buffer create. Okay. And then we need to give it the size, and this is a VK device size, which I believe is trivially convertible to a uint64. Yeah, I mean, it's just typed up as a uint64, so we're good there. And if we wanted to, we could even add a static assert to make sure that the types were the same, but I think that would be overkill right here. So we could do buffer creates. Okay, so it needs size, and then also flags. Let's see, what flags do we care about in here? We don't care about any of these flags. Yeah, these are all special use cases like sparse binding buffers, residency, alias, protected. Yeah, those are all special use cases that we don't care about. But we might in the future, so I'll just leave that at 0. Size. Queue family, so you do need to know up front what queue families, I guess, are going to be potentially touching this buffer. But you might be able to just leave that as nothing. Queue family index count, queue family indices. I'm going to look that up on the spec actually. Queue family, number of entries in the queue families array is a pointer to an array of queue families that will access this buffer. It is ignored if sharing mode is not concurrent. Okay. So if we pass in sharing mode concurrent, that means, if we pass in sharing mode exclusive, that means that we are assuming that this buffer can only be used by one queue family. And so we do not need to populate these. However, if this buffer is going to be used by multiple queue families, which is very much possibly the case, then we would have to pass these in. So, and we will do that. There's this thing called like dedicated transfer queues where you can use this hardware on the GPU. It's called DMA, direct memory access, which is something like that. AMD GPUs have this thing that's called like a dual channel DMA, where that they advertise as, which is essentially it's an accelerated pathway to upload good like chunks of data to the GPU very quickly, right? And you put that in a separate queue family in Vulkan, and you start to synchronize between these multiple queue families. And that's something we will definitely do if we're transferring a bunch of data between the two. I'm just trying to decide if we want to implement that now or wait. So the sharing modes that I have access to are just exclusive and concurrent. So exclusive specifies the access to any range or image subresource of the object will be exclusive to a single queue family at a time. And concurrent specifies that concurrent access to any range or image subresource of the object from multiple queue families is supported. Okay, so concurrent simply means that you can use it from multiple queue families. And exclusive means that, okay, so concurrent may result in lower performance access to the buffer. So if you do it as exclusive, you can technically still use it from multiple queue families. You just have to synchronize that access, right? So I think we almost entirely want to avoid concurrent access here because it's slower. And I think that's just if you don't want to sort of memorize or manage that synchronization at a lower level, which we're planning on doing. So let's go ahead and make that sharing mode exclusive. Now we need a to look at the VMA documentation again. So resource allocation. So if we want to create the buffer like we're doing right here, so we also need to populate this usage. Okay, and then I'll just leave that on the side so that we can sort of just fill this out. We're not just copying and pasting code here, we're filling stuff out so that we can learn it better at the same time. So we do still need to fill this out, right? But we also need to pass in the usage, right? And like this is what I was saying earlier, this VK buffer usage flags. You can have one buffer do everything if you wanted to. That's not necessary, and I honestly wouldn't do that, but you could if you wanted to, right? So there's different types of buffers here. Buffer usages, right? We have transfer source and destination, right? And then all these other types, like I was talking about, uniform buffer, storage buffer, index buffer, vertex buffer, and it goes on and on. So we're gonna also pass that in as a parameter and just give that here. All right. And now we need to have a VMA allocation create info. And we also have to include the VK memalloc. Probably need to include that in the header too, because we're going to need to pass in the VMA allocator right here. So VMA allocation create info, alloc create. What this is doing is so the buffer create info is describing the buffer itself, but we now need to get the actual GPU memory that's going to back this buffer, right? So alloc create and the usage. So this is where it gets interesting with the VMA allocation library because they have these different usages, but right now it's pretty much recommended that you always use the auto one because that will decide the best pool to put the memory in, or the best type to put the memory in. Now you can control whether this memory is allocated host accessible, device accessible, and whatnot. So in Vulkan, we have these different concepts of visibility, right? Like you can imagine between the GPU and the CPU, there's different pools of memory. Some are accessible by the GPU, some are accessible by just the CPU, and some are accessible by both the CPU and GPU, right? That can talk over the PCIe lane. So for example, if I allocate some memory directly in VRAM, I'm not going to be able to access that trivially from the CPU. That would be considered device local, and that's typically the fastest memory to allocate from for the GPU purposes. However, say I'm updating some data every single frame, right? Like from the CPU, I'm writing to data every frame. Well, the CPU might need that memory to be in a pool it can access, but the GPU also needs to be able to read from that same pool. That would be both device local and host visible. Does that make sense? Host visible means the CPU can read it. Device local means the GPU can actually use it in a pipeline. And then there's memory that's just host visible. This is usually just like system RAM, right? And sometimes depending on what architecture you're on, like say you're on just a pure unified memory architecture like a Mac, right? Where there's just one big pool of memory. Everything is device local and host visible at the same time. There's no memory that's just GPU and just host. And then on some other architectures, there's memory that is device local, but then there's other memory that is always like host visible and always device local, right? So it just entirely depends on your architecture and what's best. That's partly why there's this VMA memory usage auto flag, right? However, we can still control some of this, right, using this library. We can control whether we want it to be allocated to be accessible to the GPU or not, right? And there's some flags we can use, right? So let's see, we have create host access sequential write bit, allocation create host access random bit. So this is saying that the host can access this memory and it can access it in a randomly ordered fashion, right? So we don't have to do it sequentially. But if you know that you're only going to access it sequentially, then there's a special flag for that, right? And that's this one, right? Request possibility to map the allocation. If you use VMA memory usage auto, you must use this flag to be able to map the allocation. Otherwise, mapping is incorrect. If you use other value, this flag is ignored, and mapping is always possible in memory types that are host visible. Remember, we were just talking about host visible. This includes allocations created in custom memory pools. So this declares that the memory will only be written sequentially, for example, using memory copy, or a loop writing number by number, never read or accessed randomly. So memory type can be selected that is uncached and write combined, right? And that's really just an optimization, right? So yeah, that's an optimization, right? Because if you don't need random access, you shouldn't ask for random access. So by default, if we don't pass it any of these flags, it's going to create it as optimally as possible for GPU usage, right? So if we give it no flags, it's going to be device local memory, more than likely. And so that's sort of what's going on under the hood, right? So we don't have to tell it that, but if we want it to be mappable to the host, we can, using these flags, right? And so we want to be able to pass in these flags, these VMA allocation create flags. We're going to do that right here, allocation flags. Now, by default, these aren't going to be required, so we're going to assign it to 0. Default initialize to 0 here, right? And so we can actually pass in those flags. Now, usage. So there's also these other things. There's required flags and preferred flags. But these are memory property flags, right? This is VK memory property flags. So if we weren't using this VMA allocation library, then we would have to do this ourselves by passing in these flags, right? So like I was saying, device local, host visible, host coherent, host cached, right? We would have to tell it exactly how we want the memory to work, and all of that. But we do not need to do that since we're using this library. These flags can be ignored. So if pull is not null, this member is ignored. Yeah, so we don't care about that. We also don't care about memory type bits. And this lets us specify a pool that this should be explicitly created in, and the pools are actually managed by VMA. So the pools So VMA allocates a big chunk of memory, and then it puts like pools within that big chunk of memory, so that manages it for us. All right, so I think that's all we care about right now for this. Now we can actually create the buffer. I know that was like a big lecture, but it's important for understanding. And let's actually do this as a outref here. Yeah, we're gonna need to do vk buffer reference out buffer. And then we also need a VMA allocation for out allocation, right? So the buffer is the actual Vulkan object for the buffer, but the allocation is the VMA backing of that buffer. And that's not a Vulkan object. That is an object in the VMA library. However, if you're using Vulkan directly, you would create your own memory block, and you would somehow keep track of where it is in that memory block using like an offset and like a length or something, right? So there's a lot of concepts between making a Vulkan application and making an operating system that actually go hand in hand, at least when it comes to memory management here. And we can simply call VMA create buffer right here and pass all of this in. So we need the allocator, which is just going to be up there, allocator, and then the buffer create, and then the alloc create, and then the out buffer, and then the out allocation, and then the VMA allocation alert. Okay, sorry. And then allocation info, which is alloc. Allocation info, do we care about that? I don't think we necessarily care about that. Yeah, we can just pass it null for that. That essentially, it gives you some metadata if you want to keep track of that. We don't need to keep track of that. And then we'll just return if that's equal to VK success. Okay, and we will put this in the header file. Okay, cool. So now that is like that. Now we have to actually use that. So let's go and make some buffers. So we have our graphics context, which has all this stuff, but I don't think we should really put it in there. I'm kind of thinking I'm going to start a new struct here because this is sort of like the core resources for Vulkan. So let's have another struct here for, let's say, renderer context, which will hold our resources specific to rendering, right? This is more so our resources that are used in a more global sense, right? So we're gonna have a buffer here, and let's just create one buffer, and we'll call it the vertex buffer. So let's create a vertex buffer, and let's create an index buffer. And remember that function actually returns a buffer and an allocation. So let's make a new struct to sort of bundle those pieces of data together. So I'm just going to call this a buffer, and this is going to bundle the VK buffer, which is M buffer, and the VMA allocation, which is M allocation. All right, it just makes sense to bundle these together. And then in this creation routine here, we'll just return that buffer. Yeah, so the out buffer, it'll be out buffer dot allocation, and then out buffer dot buffer and buffer. And then instead of VK buffer, we have our new buffer types. Just like that. Okay, so let's have another function here. Let's call it create render context. And we're going to take in the graphics context. And we're going to return a renderer context. It's going to be called outRenderer. So let's do create buffer. So this is going to be creating the vertex buffer. Right, so we need the allocator, we need the size, which we don't know yet. We'll get into that in a second. And then the usage flags, we know the usage is going to be vertex buffer, so we're going to pass that flag in. And the out buffer, and this is just going to be outrender.vertex buffer. And then the allocation flags, which we want this to be, we want this one to be, this is going to be our device local vertex buffer. Yep, okay, and I will be back in about 1 minute. I need to get some water. And we have returned. Okay. So yeah, we're creating our buffers right now. So like I was saying, this is going to be our device local vertex buffer, right? But remember when I said that Vulkan has these different concepts of memory pools and how I just said this was device local? Well, that's going to prove to be an interesting issue here in a second, because if this is a device local buffer, right, a vertex buffer, how are we going to get our CPU vertex data onto this GPU vertex buffer, right? And the answer to that is something called a staging buffer. We create a buffer that both the GPU and the CPU can see simply for the purposes of transferring that data into this device local buffer, right? Because the other solution would be is this vertex buffer is accessible both from the CPU and GPU at all times, right? However, that'd be wildly inefficient because that's not the ideal type of memory, right? And so, because our vertex buffer is not changing very often, right? At least unless we have some like dynamically deforming vertex like landscape or something, right? But for our use case, we don't care about that right now, right? we pretty much are going to have static geometry. And so how we do that is going to be interesting, because we're going to sort of have two vertex buffers, right? And that might seem a little bit weird, but one is going to be the vertex buffer that's actually used on the GPU, and the other is going to be our staging vertex buffer. Because the staging vertex buffer, we're going to write our memory into from the CPU and then do what's called a transfer operation to get that data from that CPU staging buffer to the faster GPU buffer. So we're going to have two buffers here. One's going to be called M staging vertex. The same goes for the index. We're going to have M staging index. And we'll just call it buffer. Staging vertex buffer. Index buffer and staging vertex buffer. So, with this being said, if we have these two buffers now, right? Let's actually create them. Create renderer context, right? So we're going to create our device buffer, but we're also going to create our staging buffer, right? So in staging vertex buffer. But we need to pass in flags, remember? Those flags that we were talking about earlier, the VMA allocator flags, well, now is where they come in. So let's use those here. So we're going to use VMA allocation. VMA allocation. We want host access sequential write bit, right? Why do we want sequential write bit? Well, if we write our vertex data into the staging buffer, we don't need to like randomly access that buffer to do so. We really only need to copy it into there, right? And copying, as we know, is a sequential operation. It's not random access. And so we don't need that performance hit of random access caching, right? And so we're going to create it like that. Size is still 0, all right? So let's go ahead and define some vertices, right? So what is the first thing we want to do? We got to start thinking about our first goal here. I think our first goal has got to be getting just a triangle on the screen, right? That's what you got to do in Vulkan. You need a triangle. So what are we going to do for that? Well, we're going to define our own vertex struct here, right? And we're getting to the point where we're creating this rendering code in this file, and I think that's okay for now. We're probably eventually going to do another like little refactoring cycle where we move some of this out into a dedicated like renderer file to separate that from the gameplay logic, because you usually don't want to mix rendering code and gameplay logic too much. And we will do that, but for now let's keep it in here, right? So we're going to create a vertex struct in here, or preferably in the header file, maybe. Yeah, we're just going to call it vertex, right? And we need some data in this vertex, right? Like we need position. So let's just define another struct and let's call it position, right? Or maybe we'll call it vector, because it could be a position or it could be a direction, right? And we'll call it vector3. So let's give it 3 components here, an x, a y, and a z. And we'll put this vector in here and we'll call it in position. And we could do all of this vector stuff ourselves, but there are libraries out that could help us with that, like GLM and whatnot, and I'm on the fence on whether we'll use GLM or not. It is a common library, or whether we should do things ourselves in regards to matrices, matrix math and linear algebra. There are pros and cons to each, but GLM is pretty widely used, so we might actually just end up using that. Yeah, let's go ahead and use that. Okay, so for GLM, we're just going to add another entry in here. So GitHub repository, just like the Vulkan memory allocator, is GLM, call it GLM, and looks like the latest version is going to be 1.0.1. And let's make that available. And let's link against GLM. Okay, generation finished. All right, let's see if we can include GLM now. Yep, glm.h2p. So instead of using this vector3, all it is, it's glm vec3. And we'll call it in position. So why are we using GLM? Well, because it has a lot of math that's already implemented for us, right? Like matrix multiplication, you might think, oh, matrix multiplication is easy. There's a lot of math in there that's also not matrix multiplication that we might need in the future, right? Things like, ray intersection tests, Frustoms, that kind of thing, right? Like there's just a ton of it. And it's also, a lot of it's optimized, right? So it's not a bad library to use. It's very well battle tested. And it's also, it's fully binary compatible with a lot of like structs, right? We could just place it in the struct and it will be binary compatible. We know that this is literally just an XYZ in the struct, right? So we don't have to worry about it not being binary compatible with what we want to put in our rendering. This is literally just an XYZ struct. If we go to Vec, you can actually see this. Yeah, it has a lot of fancy declarations and templating going on. However, if you go to the actual data here, they're unions, and it's X, Y, Z, RGB, STP, right? But there's also a lot of nice utilities in this library, so that's why we're using it. Okay, so we have this simple vertex, right? And it has a position, and that's really all we need initially, is for it to have a position. And so if we go to where our staging buffers, we're now going to have a vector of vertices. We're going to call it verts. And we're going to initialize this with some verts, right? Vertex. We're going to make 3 of them for a triangle. Dot in position. Okay, so the way the coordinate system works in Vulkan is, same as OpenGL, DirectX, except that the y-axis is inverted, which is kind of silly, but yeah, that is what it is. There's easy ways to get around that, right? To sort of undo that. But yeah, normalized device coordinates, -1 to 1. So to make a triangle, let's say we wanted the triangle to sort of be like, there's a vertex on the bottom left of the screen, bottom right of the screen, and the top middle of the screen, right? And we want to specify our vertices in clockwise order, right? The first vertex we want is the bottom left vertex. So that's going to be -1 and 1.0, right? Since the y-axis is inverted, we'll end up fixing this. And then for the z, it's just going to be -1, since we're not going to be doing any clipping. Actually, we'll leave the z at 0, just because -1 is like actually literally on the near clip and it might z fight. So let's do -1, and then the middle vertex is going to be x is 0, and then y is going to be -1, since it's inverted. The top of your screen is -1. And then for the bottom right, it's going to be x is 1, and then y is 1, like this. And these actually need to move to the other vertices. There, so now we have our verts. All right, and now we can actually know the size that we need for these buffers, right? Because the size of these buffers, let's say verts size, is just the number of vertices we have multiplied by the size of one vertex, right? And then we can pass that vert size into both the device local buffer and the staging buffer. So those buffers will be the same size, right? Okay, so we have our data just in this vector, right, on the CPU. But now we need to get this vector into the, we need to get it into the staging buffer. And you may ask, well, how do we do that? And that is where we get into mapped memory. Also, you'll see that this is errored because this should only happen in the adder file. There. We need something called memory mapping. Music stopped. Let's go ahead and restart that. Okay. We need something called memory mapping, so we need to do map memory. And map memory is just going to give us, it's going to give us a pointer that we can write into, right? For a buffer. So we need the buffer to map, right? So let's pass in or we'll just pass in the whole thing, right? Const buffer. We'll just pass in our buffer struct here. And then we'll do VMA map memory is the function call. So we need the allocator as well. So we just pass in VMA allocator. So allocator, and then we need the allocation, which is in the struct. And we need, we need a pointer to a pointer. So I guess what I'll do is I'll just pass in the pointer as a ref, and this will be out mapped, right? So we'll pass in the pointer as a reference. The memory won't return anything because I don't think mapping generally fails if the buffer creation succeeded. And then we'll pass in the address of this reference to a pointer. So this is confusing, right? So VMA map memory is taking in a double pointer, right? It's taking in a pointer to a pointer. We know that, right? However, what we're passing in is a reference to a pointer. So we can take the address of that reference to sort of convert it to a double pointer, right? And that'll map the memory for us. And then we also need a routine to be able to unmap this memory. So let's go unmap memory. And I believe for this we just need the buffer. Yeah. No, we also need the allocator. Dang it. That's okay. All right. We'll pass that in too. Yeah, so this is going to be unmap memory, and just pass in that allocator and that buffer allocation. And boom, unmapped. So now when we're creating our buffers here, we can actually map our memory, right? So let's go ahead and map our staging buffer memory. So mapped staging. And since this code is getting a little bit involved right here, what I like to do if we're going to have a big function like this is to create a block embedded. It cleans up the code a little bit. So we're going to embed this in a block here. And we're just going to call this create vertex buffer, because that's the overall goal of this little block right here. So we need to map the staging buffer. Right? So we're going to call the map memory function. That's going to be taking in the allocator, and then it's going to take in our vertex buffer, but our staging one. And then we need to pass in this pointer here. And then we can say if map staging, because I don't think this can fail, but you never know, right? If it's null, you don't want to write into null memory, so who knows what edge case could cause that, but never hurts to check. And then we're going to unmap. So actually, in the future, it might make sense to, yeah, something did fall in the background, and I'm probably going to go check on that here in a second. I think my cat's knocked something down, so let me go check on that. So yeah, I'll be right back in a second. Yep, gotta love cats. All right, they just knocked over a little cup. Okay, so in the future we might not unmap this memory automatically because there's no negative really to having memory mapped for an extended period of time. If you might need to write into it again, like for example, my plan is to really just have one giant vertex buffer, right? Like the naive way would be to just create one vertex buffer for each mesh in the scene, right? But that's a bad idea for several reasons. The biggest reason being that you're creating a bunch of buffers and you're needing to bind them each for each mesh that you're rendering, right? So say you're in like a level that has like 1,000 objects, right? And each object has its own vertex buffer. Well, that means every frame that you're rendering, you have to bind each mesh buffer once for each mesh, right? That's 1,000 calls into the Vulkan library, into the driver. And each of those calls has a cost associated with them. And so we can avoid that by sort of bundling everything into one giant vertex buffer. It's all packed into one vertex buffer because all of our vertices all of our meshes are going to use the same vertex format, right? They're going to be efficiently packed into one format. So they can all fit into the same buffer. And this is more efficient because then we just bind it once, that vertex buffer once, and then we go through and we render our objects, right? So that's one technique. It's to speed up your application on the CPU side, is to reduce the amount of times you're binding resources. But for mapped memory, we can just map and unmap, since for now we're only uploading one triangle. But in the future, you can imagine, right? We might be, say we move into a new level, right? We might need to unload the geometry before and load the new geometry, right? I'm not talking about like streaming vertex data. Yeah, that would be one use case, right? Is streaming in meshes and leaving memory mapped, right? And we could totally do that, right? Streaming in assets. And Vulkan is built to do that very well. So we could do that, but do we need to do that right now? No. So we're just gonna map and unmap it right now. But in the future, we might leave this map. That's just sort of an explanation of why that is. So we're gonna unmap the staging buffer immediately after here. And then while we have it mapped, there's just one line of code, and that's mem copy. We simply copy into this mapped data, and we copy our vertex data into there. and then using the size right here. And now it's copied just like that. Now it's in the staging buffer, but we need to get it to the GPU device local buffer. And that's where our handy utility that we made last stream, the immediate command buffer, comes into play. So we can now call that immediate function. This will immediately execute some commands on the GPU so that we can do it now, right? Like we just want to run some code on the GPU right now. So let's pass in our device. And like I said, this is going to change when we get to a more complicated setup, right? Like when we get to when you're loading an actual level, you don't want to just do, okay, let's run some data on the GPU. Let's wait for that to finish, right? This is just for now, right? This is just to get a triangle on the screen. This is going to change. So just as long as you know that, right? Because in the future, what it's going to be like is, okay, every frame, do we have some data that we want to upload to the vertex buffer? We do. Okay, let's upload that and use the current command buffer that we're writing to. Let's not create a command buffer, a one-off just for this, right? And so it'll be a lot more efficient in the future. So we're going to put our queue in there, our electrical device in there, and then we also need our command pool. So remember that we have two command pools. We have one for persistent command buffers and one for transient command buffers. This is a one-time use command buffer, so we're going to use a transient command pool. And the difference is the transient command pool is simply created with the one-time use flag. Or sorry, the transient bit flag. And the Vulkan spec states transient bits is most optimal for command buffers that are going to be short-lived. And then in here, we just simply take in our VK command buffer. All right, now we can run our command. So what do we want to do? So we need to run a copy operation, right? So there's this command called VK command copy buffer, right? And so what this is going to do is it's going to take one buffer, or two buffers, a source buffer and a destination buffer, and then a list of buffer regions. And those buffer regions specify which bits you want to copy between the different buffers, right? And so we only need one VK copy region, right? Yeah, one VK buffer copy. And we'll call it copy region. So it takes a source offset, a dest offset, and a size, right? So this is pretty easy for us because we know they each begin at the start of the array, so offset 0. And then the size is this vert size up here. So we're copying the entire staging buffer to the entire device buffer, right? And we need to capture this since it's in a lambda, so we'll just go ahead and capture that by value since we don't plan on changing it. And so we can pass in our command buffer, then we need the source buffer, which is going to be the outrenderer dot the staging buffer, and then the destination buffer. I want to remember we need to do the buffer since it's a struct that we made. And the destination buffer is the device buffer. And then we have one region, and we can pass in a pointer to this right here. And we also need to capture this renderer, just like that. All right, so this is going to run, and it's going to copy our staging buffer to our device buffer, right? Now, that data is now on the GPU as of this, right? So remember when we did our immediate function, all we're doing is we're allocating a command buffer from a command pool, we're allocating a fence, and then we're beginning that command buffer. We're calling into the callback, which is the function that we pass in, which is right here. It's just doing that buffer copy. We're ending that command buffer, and then we're submitting it, and then we're waiting for that to finish using the fences that we just created, the one fence. And remember, a fence is just a way to have synchronization between the GPU and the CPU, right? So if we submit something to the GPU and we want to wait for that work to complete on the CPU, we use a fence, and we wait for that fence to complete, and then we free these temporary resources. So this is just executing, this achieves what's called synchronous GPU CPU work submission, right? It's a way to send work to the GPU in a synchronous fashion, and it's not optimal, but it works for when you just want to get something up and running, to test something, or for operations that are very rare, right? So now we can test this. So remember that these return bools, so if these don't work, we can return false. And then at the end, we can return true. Let's add some logging in here. Remember, we're using standard cout, which isn't the best mechanism for logging right now, but we're just doing that. Build to create device vertex buffer. Failed to create staging vertex buffer. All right, and then we're going to create a function. So we have a create. So we need to call create renderer context after create graphics context, right? And then we'll make that as part of this application context. And we'll call it mRenderer. All right, so let's run this, see if we get any errors. All right. So my first step in debugging is just to run through it and see if any validation errors spit out. And then we'll actually run this in RenderDoc and replay the commands to ensure that our operations are actually working. Okay, so that all ran without a crash and no validation error. So it looks like that might actually have worked, but the next step is to use what's called RenderDoc. So when you run operations on the GPU, it's really hard to debug them because you don't know what actually happened when you're on the CPU going through the debugger, right? So that's where we use a tool like RenderDoc to actually see that these operations happened as we expect them to, right? It's essentially our debugger for the GPU. So to do this, we go and we find our application. And we can say that we want to capture the very first frame because that's where the vertex buffer creation happens. And so as soon as we launch this, it's going to capture the first frame. And then we can open this up and look through. So notice how our VK command copy buffer actually ended up succeeding here. You'll notice that these buffers though have just random numbers assigned to them. And it's hard to know which buffer it's talking about, right? Like, is this our staging buffer? Is this our device buffer? Well, that's because when we send the buffers to the GPU, they obviously don't know what we called them on the CPU side, right? There's one way, and those are built into Vulkan, called debug labels, and we'll use those to be able to label these. But for now, let's see if these operations actually succeeded, right? So that command copy buffer operation happened, so we can go into here, and we can look at the region. We can see that the source offset and destination offset are 0 and the size of 36. And that makes sense if you do the math, right? Because we had 3 vertices. Each vertice contained 3 floats, and that float each vertice contained 3 floats, and each float was 4 bytes, right? So if we do 3 times 4, it's 12, and then times 3 vertices is 36. So that's where it gets 36 from, right? So So that command looked like it worked out fine. And then this command right here, vk command copy buffer to image, is actually not our code, but that's I'm GUI. It's uploading its font atlas to the GPU. So we actually can't see it because of the way that seems to be encoded, but that's actually the GUI library uploading the font atlas. So this is the one we care about, right? And so if we go to pipeline state here, I'm not sure if we'll actually be able to see this because it's not being used in anything. We might have to wait until we're actually using it to see what's going on with that buffer. Maybe we can open this buffer to view the contents. Yeah, I don't think RenderDoc lets us actually view the contents yet. Yeah. Because I don't think it actually shows transfer operations. If we go to pipeline state, there's no transfer stage here. Yeah, so that kind of just happens. So we'll need to wait until we're actually using it in a shader to debug it, but it looks like at least, you know, the command is executing fine, right? And so when we actually use the vertex buffer, we'll be able to get a better picture and see what's in that buffer. Okay, so let's go ahead and submit this. Refactor, create Vulkan vertex buffer, staging, and device buffer. And commit and push. Okay, so we have that vertex buffer, but now we also need the index buffer, which is the same exact process. So we're going to copy this and we're going to paste it and call it create index buffer. And instead of this having an array of vertices, it's going to have an array of uint32 because we're using uints for our indices. And for a triangle, that's just going to be 0, 1, 2, right? We're going to use our vertices. It's just one triangle, so that's pretty simple, and the size is going to be the indices times the size of a uint32, and then we're going to create a buffer, but this time it's not going to be vertex buffer bit, it's going to be index buffer bit, and it's going to be using indices size, failed to create device index buffer, and then this also is index buffer, same allocation flags, but staging index buffer, and then we're going to map it. Staging index buffer, and we're going to use the indices data, and then the indices size, staging index buffer, copy region, and then staging index buffer is going to be the destination, and the staging index buffer is going to be the source. And I think that is it for the index buffer. So now we have our index buffers and vertex buffers. So let's make sure that runs as well. So our program's still running, so let's close that out, and then let's run it again. All right, and let's continue. we do get a crash right here, actually. And that is because we forgot to copy and paste right there as well. Another crash. That should be M index buffer. All right, and the crashes are gone. And now, one other thing I want to do is we talked about the debug labels, right? Is I want the debug labels to show up well in RenderDoc. So let's do debug labels. So I have to look up the documentation on that real quick. Yeah, so it's going to be called set debug details object name. So this is, since this is an extension, we actually have to load it as a function here, right? And so one thing I want to do is load these extension functions here. So when we create our graphics context, we're going to load these debug functions, right? So if you see in like our destroyed debug messenger right here, we're doing that same thing where we're loading the function. So let's go into our graphics context, and we'll just make a new struct here, and we'll call it, let's call it Vulkan functions. And then we'll make a entry maybe at the top, and then we'll call it mVulkan functions. So the one that we need is it's going to be okay. So in the Vulkan loader, there's this convention that the function pointers are prefixed by pfn, which is pointer to a function. So the one that we need is called vk set debug utils object name. And we're just going to call that vk set. Yeah, we're just going to leave it at the same name. And I don't think these have been promoted yet. So vk set debug, actually they have, it looks like. Oh, no, they haven't actually been promoted. There's just function pointers for them. So yeah, we still have to load them ourselves. So yeah, we still have to load them. So vk set debug utils object name. There's also a set debug tag. Arbitrary did it to an object, so we don't want that. We just want to be able to set the name of the object. Okay, so when we create the graphics context, we are going to populate these, maybe at the bottom right here. Populate Vulkan functions. Yeah, and then graphics.m Vulkan functions, this one. And we're going to set that to loading the function, which is just this right here. pretty long line of code, so I'm gonna split that into 2 lines. And then pass in the instance. And it's loaded. Okay, so let's see if this actually loads. Let's run this. Yep, so it loads, so you can see that the function has a value right there. It's not null, so that worked. So now we just need to actually be able to set names of objects, right? And it would be annoying to have to call a function using that every time, so we're going to sort of create a util for this, right? And we're going to create a macro because we don't want to set the debug name of an object if we're like in a production environment, right? First, because we don't really want people being able to easily reverse engineer our graphics commands if they capture it in render doc. And secondly, it's just performance, right? Like we don't want to do unnecessary things like that unless we actually intend to debug it ourselves on the GPU. So let's first create a function, and here, say debug, and let's say void set debug object name. And then what we need is we need the function pointer to the vk set debug utils object name, set object name function. And then I think the way this function works is we need this info extension struct. So let's say object name info, right? And the type is oops, object name. Okay, so it needs a handle, it needs a type. Okay, so it actually does need an object type, so we're going to use some template magic. We're going to use the magic of template programming to solve this problem. Okay, so we are in the header file here, right? So this function is going to take a template and it's going to take in the object that we want to set the debug name for, right? Because the reason why we want to do this is because if you look in here, this takes an object type as an enum, and it's kind of annoying if you have to pass that in, right? But if it's inferred by the template, then we can use compile time intrinsics to sort of extract this piece of information right here, right? So if we come and we do the vk object type up here, object type, first of all, we can do a static assert on this template parameter and say that standard is same value, right? Make sure that these are the same. Essentially limit it, throw a compile time error if it isn't. And where's that at? Where's standard is same? Standard is same v. That's going to be in the type setter, metaprogramming library. Yeah, so this is a little bit of template metaprogramming here, guys. So we need to include type traits, right, for this template program. All right, and what we need to do is standard is same if t is the same as, let's say, vk buffer, right? We have to assert that it is a buffer. And if it's not a buffer, we're going to say that type is not supported for this template function. Type not supported. So that's a nice way of throwing a compile time error, right? You'd rather it fail at compile time than runtime. That's why we're doing that, right? Now, after this point, we know that it has to be at least one of these, right? And the only one we're supporting right now is vk buffer, so we know it's vk buffer, but we'll support more debug object name types soon, right? So we're going to say if const expr. If you've never seen a const expr if statement, it's an if statement that is evaluated at compile time, right? So the expression inside of it has to be compile time evaluable, right? And in our case it is, because we're simply saying is same v again, right? And maybe we can do this up here, right? We'll do const expr bool, let's say is buffer, right? And we'll say that is buffer, and then we have to static assert that it is a buffer, and then down here we can say if const expr is buffer, then, or I don't think you can do, can you do a const expr switch statement? Because that would be ideal right here. Const expr switch. I've never tried this before. Moreover, discards. Those are guarantees I think you would expect from a true switch const expr. Yeah, I don't think that there's a const expr switch at the moment, maybe. Wait, yes, there is. Switch const expr. Okay, so there is. Switch const expr on the object type T. Wait, but I can't do a switch statement with template types. That's the next problem. So can I do a switch const expr on, well, it is already the type. So switch on template type C++. Can you do that? This might be, yeah, I don't really think that using this is going to be possible. It would be nice to have a switch const expr that switches on the template type expression, but we're not going to use that. It's a little bit complicated, but we're just going to use if const expr on is buffer, and then vk object type can just be up here, and then the object type, and then if it's a buffer, the object type is going to be equal to vk object type buffer. See? And then we need to actually pass in the object, right? So t object. So it's not useful unless we're actually passing in a template parameter here. So we're passing that in. So the object type is now set to object type. And then we also need object handle. So this means that this object needs to be convertible to a uint64, right? So we need another assertion here, right? Standard is trivially assignable, maybe, or constructible. Which one do we want? I think we want trivially assignable, or maybe, let's see, C++ template, check if type can be casted. What is the meta to see if it can, is constructible? Is convertible, that's what we want. They do have is convertible. Is it trivially convertible? No, is convertible. So we want to make sure that a T can be converted to a uint64T. And that's pretty much guaranteed by this, but it's always nice to have this extra insurance. Type is not convertible to uint64T. So now we know that the type is the type that we expect it to, and that it's also convertible to uint64T. We know that it's 100% safe to just static cast that type to a uint64T object. But I think we actually want to rename this to handle. Yeah, that's actually a handle. So now the object handle is passed in. Now we just need to pass in the object name, right? So this is going to be a constant standard string, and this is object name. And object name is going to be that C string right there. So we have the object name, the handle, the type, and we don't need that. So now what we can do is we can call this setObjectName function. It returns a VK result. That's so weird. I think I'm just going to ignore that. So we're going to cast it to void, because if it fails to set the debug name, I mean, we're not going to fail the application, obviously. So we're going to pass in the device as well. VK device. And then we just need to pass in this object name info. So there you go. You have some template meta programming to do some Vulkan stuff. All right, now what we can do is we can take this template and we can go over here and we can actually use it now to set stuff. But we'll have to pass this in every time we call that. That's kind of not very ergonomic, right? So we probably want some sort of helper function in here to set debug name, right? So yeah, let's device. Yeah, okay, we're definitely gonna do that because it takes two things from the graphics context, right? So we're gonna sort of do a forwarding template here. So template type name t void set debug name, and then t handle, but it also takes in the graphics context, and then the name of the object. And we're simply just going to forward this to the graphics layer, right? Set debug object name. And this is going to be called set debug object name. And then we're going to pass in the Vulkan function, set debug object name, function pointer. Actually, first is the device, right? And then we need the handle and then the name. And then we're just forwarding the template, just like that. So now comes the magic. If we go into create renderer context down here, after we create the buffers, we should be able to say set debug object name, passing in the graphics context, and then passing in the graphics vertex. Or sorry, renderer, right? Outrenderer.vertex buffer. And then we'll call this vertex buffer. So on the debug name for this object will be set vertex buffer, right? And then this one will be called vertex staging buffer. And then for the index buffer, this one will be called index buffer. And this one will be called index staging buffer. Let's see if this burns and crashes or not. Run. Compile error, probably somewhere in the templates. Static assert failed. Type not supported. And I know why that is. It's because I'm passing in the actual buffer, our sort of utility buffer instead of the actual buffer, right? So what we need to do for that is just simply add a dot buffer at the end here. So that's where our compile time program actually came in to save us right there. And run. Another error. Now it says type is not convertible to uint64t. Okay, so that means that that makes a little bit more sense. So type not convertible to uint64t. So it is a VK buffer, right? Okay, so it's a non-dispatchable handle, which is defined as a struct pointer. Okay, so of course a struct pointer is not convertible. So we will need to remove that checked, right? What we're really just doing here is reinterpret casting this, right? We just want to reinterpret cast that to that struct pointer to again 64 T here is what the Vulkan API wants, I believe. All right, so we got it to compile. So let's step in here and see what happens. So it forwards it in. So notice how in the stack log right here, our template parameter is a VK buffer, is what's passed in, and our const expr was evaluated at compile time, so we can't debug that. But we're down here, and then it ran. Any errors? Nope, no errors. Click continue, no errors still. Cool. So now we can actually test by capturing on render doc to make sure that this uses our debug names now, so that we'll have a pleasant debugging experience. Capture the first frame. Expand this, and boom, look at that. Now, this buffer is not correct, but look at how the index staging buffer shows up, and the index buffer shows up. The vertex staging buffer shows up, but not the vertex buffer. That tells me that we made a little typo over here. And yes, we did. Vertex staging buffer. Let's run that on render doc again. And there we go. Vertex staging buffer, index staging buffer, and index buffer. So we now have nice debug names when we're using third-party tools to debug our application. And with that, I will be back in 1 minute. And we are back. Okay. So now that we have our nice debug labels, we can move on to the next thing, which is what's called pipelines. And this is hard, but this will involve a little bit of work. But as you see, it's a lot of work to get a triangle on the screen. Vulkan, we don't even have a triangle on the screen yet. So when people say Vulkan is verbose, it's not a joke. Let's see, how many lines of code we are at? So in our main file here, we have 575. And granted, we're doing more stuff than is expected to write a very simple Vulkan application, you know, with the future in mind. A little bit of architecting and whatnot, but, you know, not too overkill. We have 575 lines of code here. And then in our main sort of Vulkan file, 363, and then command, another 100. Another 60, and then in our swap chain 184. So you're looking at about 1,000 lines of code and still no triangle on the screen. But I think the pipeline is the next big thing, and that will pretty much be the point where we can have a triangle on the screen, I think. And then things start cascading really quickly because you can start doing a lot of stuff really quickly after you have that. Because yeah, you're doing a lot of stuff up front with Vulkan. So let's look at pipelines. And let's commit this code. Debug labels for objects allows to show friendly names when using third-party tooling. Okay, so I want to make another file, and we're going to call it graphics pipeline. Okay. So graphics pipeline is going to be the file we use for all of our pipeline related functions and structs. So a pipeline in Vulkan is this giant object. And when I say giant, I mean giant. there's like 10 or 20 different structs embedded that you have to fill out for a pipeline. It contains all of the state for rasterizing, right? In the case of a rasterization pipeline. Or for a compute shader, it contains all of the state needed for a compute shader, or for ray tracing pipeline, all of the state needed for ray tracing, which we're not doing right now, but we're just doing rasterization. And then we'll eventually move to compute. But as you can imagine, there's a lot of state involved with rasterization, right? You have blending operations. You have, what is the layout of your vertex buffers? What is the layout of the data in your shader? What like kind of depth testing are you using? Do you have a depth buffer? Are you using multi-sampling? Like stencil buffers, right? There's like a billion different things that you can imagine as part of a rasterization pipeline. And you have to fill out every single bit of that in Vulkan. Now, some of that is dynamic, can be dynamic, but we have to start somewhere, so we have to start by filling it out. So that's what we're going to do right now. So we're going to start. This is a journey. It's going to be bool create pipeline. This is where we're starting. So to create a pipeline, I have to check the documentation for this one. So create pipeline. So the first thing we need to do is fill out what our vertex input binding description looks like, right? So vk vertex, well first, let's do this a top-down approach, right? vk, let's include Vulkan. Let's do vk pipeline create info, or pipeline, what is it? VK create graphics pipeline is what it's called. Yeah, so it's VK graphics pipeline create info. This is basically just a rasterization pipeline, right? So graphics pipeline info. So look at this struct. It has a bunch of stuff that we have to fill out in it, and we have to fill out pretty much everything in here. So let's start from the top. Of course, we have to set the type. So graphics pipeline info dot type equals graphics pipeline create info. And then we need to tell it about our shaders. Okay. The next thing, shaders, right? We have to load our shaders from disk, which we're not doing right now, right? So do we want to do that, or do we want to do this graphics pipeline first? We could do either or. Let's do the shaders first, since that's kind of, I guess, harder, but not too hard. Kind of hard, because we have to use the built-in shader tool that I was authoring. Okay, so I have the shader tool called Shadersmith, which we need to use, right? So right now, let's do this. This will be the simplest way to do it. So at startup, we're going to run this tool to compile our shaders, right? And so let's say, or maybe we could even do this as like, yeah, we could even do this as like a command line batch file that just gets run every time our shaders change and we want to update them. That actually would not be a bad idea. Yeah, that might not be such a bad idea, actually. So if I have the tool, the question is, do I just want to copy and paste it? I could just copy and paste it. Do tools, copy it and paste it in there. Call it, yeah. So if I have my shader smith tool in here, and then if we have a new folder, let's call it shaders, right? So we'll have our shaders in a folder called shaders here. So let's create our first shader here. We're going to call it simple shader, and we're going to call it dot vertex, right? And simple shader dot fragment. So we're going to have just a basic vertex fragment shader here. We're sort of bootstrapping this tool right now, okay? So first we need to define the OpenGL or GLSS version. I think actually I want version 450. And then we need to define the attributes. So location equals 0, input, vec3, and this is the position. And then we need the main function. And then we'll just set the GL position equal to this with 1.0, yeah. And then for our fragment, oh, I got those mixed up actually. This is the vertex. And then for our fragment shader, this just has to have an output field, and it's going to be a vec4 for frag color, and then we'll just set the color to like red for now. We'll just make it red. Okay, and now we have to, my tool expects there to be a JSON file at the root, so we're just going to call it shaders.json. And there's just a shaders thing, and it's just an array, and it contains your shader name. So simple shader.vert, and then simple shader.frag. And then at the root of our project, we're going to have a batch file, and it's going to be called build shaders. And it's going to compile all of our GLSL into Vulkan intermediate representation, also known as SPIRV. I need to save this as a batch file. All types, build shaders.bat. Okay, and I want to delete that old one. Okay, so build shaders.bat is just going to do, it's going to go take the tools and the shader smith standalone.exe. And then I need to review that tool to, okay, so if I just run this right now, it should tell me what the expected command line parameters are. So I open a terminal right here, and then I do this build shaders.batch file. It says invalid usage, correct usage, source directory, output directory, and build type. Okay. So we're going to pass in for the source directory is going to be the shaders directory. And we'll do it relative so we don't have problems with other machines. And then it's going to go into output. This is the only issue is I want this to work for all configurations. So maybe I build the shaders here Yeah, I might build the shaders here inside the source directory, because the built shaders, maybe they're actually a part of the source for now at least. We could always change the way that works. Yeah. So maybe, do I want to put it as adjacent? So maybe the output directory will be built shaders. Yeah. And then the build mode, let's just make that development. So if we run the tool now, I get an error. So that's interesting. That means that there's something that went wrong in the actual tool itself. So now I have to open the tool so I can do some debugging on it. You know what? There's probably an error somewhere like around here, because I don't think I've actually tested this standalone. So the source directory is 1. Yeah. Let's create a test launch configuration here. So if I go to project, or debug and launch settings, let's do some args here. Actually, I need to pass in the JSON file. Yeah, I actually have to pass in the JSON file for the shaders. So this needs to be shaders and then shaders.json. Yeah. Okay, there we go. That actually worked. And then in built shaders, there's just one shader, so that's kind of weird. Oh, you know what? Okay, so that's because this is actually a bug in the tool right now. So if you have two shaders with the same name but different extensions in the source, the output will actually map them to the same location in the built shaders. So I'm gonna have another batch file here for clean shaders. And clean shaders is going to just do rmdir built shaders. Directory is not empty. Okay, let me look up some options for this command, because I don't care if it's not empty. Okay, so /s, I believe is what I'm looking for. /s/q maybe? /s/q. Alright, cool, that removed the directory. So that's cleaning that properly. And then build the shaders. Builds them. But of course we have that bug right now, so I have to fix that now. Okay, so let's go into ShaderSmith and let's fix that bug. So this is going to be in the compiler. So the output directory is I'm doing it as a is doing the stem, but I'm not incorporating the existing extension in any way. And I think to fix this, I just need to incorporate that extension as part of it. Right? So this could probably just be the .file name, that string. Yeah. And then I'm just appending a .bin after the end, right? So if it's simpleshader.vert as the source, it then becomes simpleshader.vert.bin as a result, right? So before I was just taking the stem, which was the part before the extension, but now I'm taking the stem and the extension plus .bin. So let's see how this works out with our existing test cases. Let's go into here. Let's go to our output, install, and let's delete the existing ones, and let's run this and see how this does. Did it not do anything? Oh, that's right. That's because I need to run test. Not that one. Okay. Let's see. Okay, so you can see now we have .vert.bin. So cool. So it's using the extension and stem put together. So I'm going to now test that. However, I need to copy over the updated tool. Since we're our own customer of this tool, we essentially just copy the tool's output and we paste it into our project because we're using our own tooling essentially. And then so let's clean the shaders and then let's build the shaders. And boom, now you can see there's two shaders and it uses .vert.bin and .brag.bin. That's exactly what we want. So let's go ahead and commit the change to ShaderSmith first. So we're going to do git commit. If you see, we can view the compared with the unmodified, so we can see exactly what changed. Just a small change right here, right? So we can go ahead and commit that and say incorporate the shaders stem and extension to produce the output binary to remove the chance of output file name collision. So that's basically just a little bug fix right there. And we can close out of this project again since we don't need to modify it. Now for this project, we have started adding stuff like build shaders, clean shaders. Can I just run this from Visual Studio? I don't know if I can. All right, so does this still compile? Yes, it does. Okay, so we're gonna go ahead and submit this because this is adding some stuff, quite a few things. So we've added 2 batch files. We've added our test shaders. We've added our built shaders. I'm trying to decide if I want to submit those built shaders to Git or if I want to require those to be compiled every time. Because those are technically binary files, and keeping binary files like that on Git might not be the best way to do things. I'm thinking that maybe every user should actually compile these shaders, every developer, but maybe not though. Maybe it is okay to submit them because they're pretty relatively small files. They just need, the main problem is they have to be updated, recompiled every time a shader changes. So there is that. Now My tool doesn't have file change detection yet, like to compare the bin timestamp against the source timestamp and recompile if necessary. That is a feature that I would hope to add soon. It's not too hard to implement, honestly, but that will be left probably for next stream. Do I want to submit these binary files is the question. I think no, I don't want to submit them right now. So I'm going to add them to the get ignore file. And what we're going to do is going to say add a section here, ignore compiled shaders. It's a built shaders. The built shaders, every user is just going to run that command. That if you're a developer, you run that command, and you're going to get your built shaders, and you're going to be able to run the game if it's in source format. Because I don't want to submit the binary files. Later on, we might automate this a little bit more cleanly, maybe remove the need for these batch files, but I like this for now, as long as we're not submitting these to the repo. So if we do git commit now, you'll notice that since I added to the get ignore, they're no longer listed here because they're getting ignored. So we just have the graphics pipelines, you make list, and the shaders we added, plus these 2 batch files, which I'm completely fine with adding. So add batch files to compile / clean shaders, add shaders.json plus 2 test shaders, start work on graphics pipeline. That's what it is. And commit and push. Cool. That has been pushed. Just checking out the GitHub organization right now, seeing how the commit history looks. It's always fun to look at the commit history. $30 commits already. Wow, I've already submitted a lot of stuff. It's not too bad at all. All right. So now what we need to do is we need to load these shaders, right? So we have these compiled to binary. Oh, well, first things, we built the shaders, right? And we put it in a directory. We actually need to install those when we're installing our product. We need to install the built shaders into there. So to do that, we're going to do install directories, or directory, built shaders, and the destination is going to be in the root of our install. Well, actually, we're going to put it in /shaders, right? Because the built shaders are the only shaders that matter. We're never going to be shipping the source shaders with our actual game, right? There's no reason to ship the source. We only care about shipping the binaries, right? So we're going to install that directory. So if I run that, it's going to now say, hey, cannot find those files, cannot find the built shaders. And that could be because we haven't compiled it, or that could also be because it just didn't name it right. So if I run it again, get the error, built shaders, okay. Oh, okay, that's because built shaders is actually up a directory, right? Yeah. So let's do the root directory. We're going to install the built shaders, just like that. All right, and it ran that time. So let's see if the built shaders actually got copied over. So output, install, shipping, and you can see the built shaders did get copied. However, they got copied into another directory inside shaders, right? And by the way, this is our install target, so it's like a minimal. It just contains our exe and a few other resources that we need, right? So I don't want that directory to be like that. So I believe what I can do is I can just add a slash in front of it, and maybe that'll fix it. So if I delete that, and if I run it this time, there we go. So now you'll see that our compiled shaders are just in the root of our install directory. So now we have to load these, right? And this is where things get interesting, right? So yeah. Yeah, this is where things get interesting because I actually need to use my tool, but I need to use the source code of the Shadersmith tool. And I've already separated it out to sort of allow for this use case. But what we're gonna need to do essentially is, because I want to load all of these shaders, I want to load that definition file, right? And I want to read that definition file so I know what shaders to load. Yeah. So what I need to do is in our install, we also need to install a single file here. We need to install our shaders in our shaders JSON, and we're going to put that in our shaders directory, right? Because we need that JSON file still. So see how that's now copied into our install, that JSON, because that contains all of the definitions of our shader. Now, we need to add a source code dependency on the Shadersmith tool. So we're gonna do that like we've done everything else because it's on GitHub. However, we're not going to do this sort of like on a tag because I literally just made this tool. We're depending on our own tool, right? We're just going to use the main branch, the latest submit from the main branch, right? And let's see here. So let me get that latest commit hash. And we're just going to say this is master, right? This is master of Shadersmith. Right, and let's make it available. Okay, and then we also need to link to it. So let's link to it down here, Shadersmith. So notice how I've separated this out into a few different targets. So we only need the Shadersmith file target because that's the target that loads the file, but doesn't do anything else. Yeah, it just reads the shader file. And that's going to depend on another dependency called enrollment.json, which we might need to also pull in. We'll see. We'll see. This is pretty simple right now, as you can tell. But we'll add more stuff to this as well. Okay, so if I link to that tool and then at launch, let's include the shader smith. So I made it a static library. Oh, okay. So I didn't give it a include directory. That makes sense. I think I need to do that. Yeah. Target include directories. Shadersmith file. It's going to be a public, and it needs to be cmake current source directory. Right. Let's commit that. Add target include directory for shadersmith file target. And let's also change our cmake list here to the latest commit hash. Okay, so can I include it now? Yes, I can. Success. All right, include shadersmith file. All right, now what we can do here is we need to sort of define like an implicit directory structure, right? So this is sort of where I think we should start splitting this out to multiple files. So I'm going to add another file here. Let's call it like shaders. Or no, maybe I'll call it vortex shaders. Yeah, I'll stick with the naming convention. Okay. That's weird, they're like defocused. I do not know why that's defocused like that. That's so weird. Okay, so in the shaders, we're gonna have a sort of a functionality here that loads all the shaders. Yeah. Oops. Yes, we're gonna have a. We need to load all of the shaders at once, right? So how do we want to do this? So we're gonna have a struct that probably contains all of our shaders, right? And they're just going to be VK shader modules probably. Yeah. And then we'll say what kind of shaders they are, right? So let's say in simple vertex, and let's have simple fragment. And we're going to have a function that loads all the shaders. Actually, we're going to do this a little bit more dynamically. This is going to return a, let's include unordered map. We're going to map a string to a, include string. We're going to map a string to a VK shader module. And this is going to be out shaders. But it needs a string for shaders definition. Or we'll say shaders JSON file. Yeah. Yeah. Okay. So now we can include the shader Smith. Well. Fix this up first. Okay. Now if I include shader Smith, still can't, that's weird. Okay. Okay, now I can do shader, what's that namespace? It is shader Smith. Okay. Shader Smith, and now I can read the shader file. Okay, so I need to pass in the shaders JSON, and now I just need the out file. So if not, shader Smith file, shader file. To read shaders. Okay. So now we've read the shaders JSON file. Now we just need to actually process this file. Okay, so it's just a vector of shaders, which is a name and a list of Ubers, but we're not using Ubers right now. So what we want to do is we want to go through each of these for const shader through the shader file shaders. So it's kind of a name, but we need to sort of know where the shaders are loaded. So we need to get the path of the shaders directory, right? Which is going to be, oh yeah, actually this is easy. So it's just going to be whatever the path is that was passed in. Let's say shader source directory. Yeah, it's just going to be that, the parent directory of that. Yeah. It's going to be the parent path of where the JSON file is stored. And so now, when we're going through here, we can say the shader binary is equal to the source directory with the relative path of the shader name. Now, if we get into Ubers, this changes a little bit, right? Uber variables, which we will get into later. Uber variables is essentially a way for creating multiple permutations of the same shader using a bunch of different input parameters, but we're not dealing with that right now. So we're just going to we're not going to account for Ubers, right? So shader binary path, we want to make that canonical. So let's make that canonical. And then we need to load that binary file. So do I have a way to read a binary file in here? I do not. I think that can just be part of the ShaderSmith API though. Is there a read binary? Or is it load binary? Load binary. No, because I had an output binary file, but I never had a load binary file. Okay. So I need a read binary. String binary path, and then we're going to include fstream here. And then we need a standard if stream input shader binary. That's going to be the binary path. And then we need to open this with IO space binary, since it's an input binary file. Okay, So what we need to do is do some reads on this binary file. Well, my navigation sucks on this file. So I'm just gonna have to use the C++ SDK for this. Okay, standard if stream read. Extracts end characters from the stream and stores them in the array pointed to by S. Okay, so essentially we just need to read the binary file in a bunch of blocks until we've reached the end of the file, I think. Yeah. So we're just going to do while we read this, and let's say car, and this is going to be block size. Let's just say it's 1 kilobyte. And then we'll read this binary file. We'll put it in the block. And standard stream size. This is going to be the number read, I think. Oh no, the number of characters to extract. Okay. Yeah, that's interesting. So it seems like the normal way to read a file isn't to do this block-based reading, but you can do like a seeking. So if you do input shader binary dot seek to the end of the file, and then you can actually get the length of that using tell. Gets you the pointer. Static member access through instance. That's so weird. Okay, and then we can seek back to the beginning. Oh, that's actually and then this is dot beg to the beginning. So that reads length of file. Okay, and this is going to return a vector of yeah, we're going to return a vector of cars, and this is going to be the out file. And we're also going to return bool. If not, if this stream isn't open, then we're going to return false right here. It means it failed to open. So we seek right here to get the length of the file, and then we're going to establish the file buffer. Which is a new character dynamic array. This is going to be file length. And then we're just going to read it directly into that buffer right there. So dot read into the file buffer. How much do we want to read? We want to read file length. So it reads the whole file right there. And then we can actually have an additional error code right here if part of this fails. This wouldn't have making set file at this point. Yeah, I know. Yeah. It seems kind of silly that I have to do all this to get the size of the file, but yeah, it's like why can't that just be a function? Like, just give me a function. It's like it's like a lot that with a lot of things in C++ too. Like with some string things, like if I want to like split a string, and parse a string, it's just too complicated. It's like, come on. So get the file length, read that file into the buffer here, and then we actually have to do some more error processing here. So it's possible that, yeah, so it could have failed, right? So if not, right, this will essentially return, if this is, if this casting this to a Boolean is failed, right? Well, what does this say? Cannot convert to bool. So this should be convertible to a Boolean. Possible let's do that. Oh yeah. Oh, this is standard stream position. Okay, so if not, then this is an error, and we can return false right here, I believe. Or, well, let's just return this cast to a bool, since that contains the state of whether this succeeded or not. So. Okay, yeah, I don't know why this is giving me the red squigglies right now. That's kind of weird. Okay, but now I actually need to take this memory and copy it out to this vector, right? So let's go ahead and resize this output vector, and we're gonna make it equal to file length. And then we're going to do standard copy n. And the first is going to be equal to outfile.begin. And, well, actually, the first is equal to file buffer. And the count is equal to the file length. And then the destination is outfile.begin. Will this work is the question. Oh, it looks like it does. So in C++, a pointer is actually, can be an iterator, right? So we're taking the beginning of this vector, which is an iterator, and we're taking the pointer, which is also an iterator. And that should be able to copy it out. And then after we copy it, we delete this temp file buffer, right? And we need to make sure we're putting this in a scope, just so it makes sense that the scope of this dynamic memory is from here to here. Let's call this load binary file. And this will probably be moved into like a utilities file of sorts. Okay, so if load binary file shader binary path and then standard vector shader binary data. So if this fails, we continue. We'll skip the shader, but we'll print out an error. Actually, we'll return false, because if one of our shaders fails, that's pretty catastrophic. So, and then return true if all of them succeed. Failed to load shader. Okay. Okay, so but otherwise, we have our shader binary data that has been loaded successfully, and we need to do something with it, and that's the next part. But let's see if this actually loads everything first. Well, we're not actually calling it yet, so it's not going to do anything. let's include that shaders. And then after we create our graphics context, we'll load our shaders. So, okay, so now we need to pass in the file path of the JSON. So we need to do some extracting, and this is a little bit platform dependent because we have to get the path of the exe, right? So we need to get the root path of our games directory, right? And this is platform dependent, surprisingly. So C++, I don't think there's still a way to get the path of the current executable. Now let me look that up and make sure that it's not possible. Yeah, no, that's still not possible. So like, for example, in Linux, you would use /proc/self/exe to get that, but that's platform dependent. So what we're gonna have to do is do this, right? So if defined win32, well, we need an else, and then end if, and then we're gonna put an error platform not supported, right? So we'll need to support the other platforms like Linux and Mac for this function because this is a platform specific function. But for Windows, this is simple. So let's say we'll have a max length of 512. It's get module, and we also, oh man, I hate doing this. We need to pull in the Windows library. So I'm going, because I do not want to pull in the Windows library to this because that's annoying. So we're going to add another file called platform, or let's just call it, I don't know, utils, right? Or maybe vortex utils, yeah. Vortex utils.h and vortex utils.cpp. And the reason is I don't want to pull in the entire Windows library just for this one thing, right? I want to keep that very much so contained into its own CPP. I'm going to do that. So if defined win32 vortex utils.h vortex utils.cpp. Right here, we're going to include Windows, the Windows header file. And then this function that we're writing right now, to get the root path, is we're just going to put that in the utils. Yeah. Now we can do get module file name A. We're going to keep this to ASCII. Pass a null for the module handle, and then pass in the module path. And then for the array size, we can do this compile time macro to get the compile time array size, so we're not repeating ourselves. Like that. And then we can simply just return the module path. Well, actually, let's do this. Standard file system path, exe path. This is going to be the platform dependent function right here. Get executable path, right? This is platform dependent. And then get root path. Is not platform dependent because it's simply going to be the executable path and the parent of that path, right? The parent of our executable is the root path. And then our shaders directory, get shaders path, is going to be the root path slash shaders. And then the shaders JSON is, see how we're just sort of reusing these functions here? The shaders JSON path is going to be the shaders path slash shaders.json. And then why don't we also just move our load binary file into this utilities file while we're at it? Because I can see that being used outside of just shaders. That can be used for any kind of thing. So load binary file, put that right there. And then we also need to include some stuff. Okay. All right. So now, load shaders. We can actually, the shaders JSON is just get shaders JSON, but we actually have to include the utils file here. Vortex utils is get shaders JSON path dot string, and then we need somewhere to put these shaders in, right? So why not just put these in the renderer context? So it's going to be an unordered map. Let's actually make a typed F for this so it's not so long. A VK shader module to standard, or it's going to be a standard string to a VK shader module, right? Because it's string to shader module. Shader map. We're going to call it shader map. So the shader map is just going to be M shaders. So now down here during load shaders, we just pass in the app context.render.shaders. And then failed to load render shaders if this fails. So now load shaders should be called. Takes a D word, so we need to cast this to a D word for the Windows Git module file name. Okay, so let's see if it reads the shader file. So it passed in for the directory install shipping shaders.json. That looks correct, and it did load it. And notice how in the shader there's two vectors, right? So it did load our JSON correctly, because you can see there's simple shader.burtonfrag, so that's good. So now it gets the shader source directory by going up a parent, and that looks correct. And now it's going to go through every shader in there, and it's going to create the path, convert it to a canonical, and that's our first crash. That means that the file didn't exist if it couldn't canonicalize it. So let's see, simple shader.burn. Ah, okay. That's because we have to change the extension. So let's actually make this a part of Shadersmith, right? The file naming conventions, right? We need to essentially be able to know what the extension of a shader is, right? So let's do, because for, depending on the target platform, right, it might be a different extension, right? Say if we're on Metal, maybe it's .msl for the output shader, and if we're on Windows or Linux for Vulkan, it's going to be .bin, right? So we're going to do this in Shadersmith. Get shader bin extension, right? And for now, we're just going to return .bin. Well, okay. Yeah, I do want to put it this right here. you need a return .bin. And let's use that in here. Get shader bin extension. And then let's make sure that still runs. Alright, cool, it still runs, and let's commit that. Add function to get the shader binary extension. Yep. Now let's go back to our thing and let's update our commit hash here. Because now the binary path is going to be the shader.name plus shader smith get shader bin extension. Okay, and as you can see now it's simple shader.vert.bin, and let's see if our load binary file function works now. Okay, so it's going to open up the input stream, and let's see if it's open. It is open, so that means that it at least found the file. Let's see, what is the file length? It seeked it out as 976. So let's go to Windows and see what the actual file length is to see if that looks accurate. So let's go for the vertex shader properties, and yep, 976 bytes on disk, so it looks like that is accurate. And now we're going to create a new character dynamic array of that same size, and then it's going to read that into there. And would you look at that, the array does look like it is filled with binary data now. I think we can go view this in memory. We should be able to open this up. There should be a memory viewer. Debug, Windows, so I can view the raw memory here. Yeah, memory, let's do memory 1. And now if I remove this, should be a view in memory somewhere. Using the memory window, let's see, open a memory window. Under debug Windows memory, move around in the memory window, customize. Maybe if I just oh yeah, I just punch in the address. You basically just punch in the address that you want. Oh yeah, there you go. And then you can copy it, and then you can just paste it right here. And then it takes me to where that is in memory. So as you can see, we've now navigated to where the shader binary was lit into memory. And it makes perfect sense, because if you look at the raw memory here, you can see various intrinsics, such as GL per vertex, point size, clip distance. So this is clearly a shader binary right here being loaded into memory, and you can see the various things like target environment, SPIR-V 1.6. All right, so you can see that it looks like it was loaded successfully into memory here. And so now it will resize the vector with that same length, and it'll copy it and delete it, and we're off. Now, here's the bug. If you're keen C++ knowledge, you'll know that there's a bug right here. And it's actually a pretty bad bug. See if you can find it. Just kidding. This delete right here needs to be delete array. Otherwise, it's not going to delete the whole thing, and that's going to be a memory leak. Well, yeah, that was not the correct delete anyway, so that's why there was the squiggly right there. So that needs to be delete array. So yeah, so let's now, so that works, that function. So let's see if the rest of the shader is loaded, the other shader. Okay, now, so if I go next and go, and then it looks like, yep, the binary data was filled up, size 976. Cool, but we're not doing anything with it yet, but we will be here shortly, and that's loaded up, and cool, so that succeeds, and we're running like normal. Now let's actually do something with this binary data. So we need to basically compile this into a Vulkan shader, or not compile it, it's already compiled into SPIR-V. Technically, it still needs to be compiled into GPU microcode, which is the ISA code, right? GPUs have microarchitectures, you know, SPIR-V is just an intermediate representation. And so we need to do that, right? And that's going to be through the shader module interface in Vulkan. So I think it's vk create shader module is what we need. Yeah. So we need to do vk shader module create info. So shader create. Oops. So type is going to be structure type shader module create info. And that needs a code size, and this is just the length of our vector. And I'm actually thinking about a way to make this faster, right? Why would we copy it into a vector if we can literally just pass in the, let's say we pass in as a double pointer, right? Let's do a character pointer reference out data, right? Why not just do that? And then the responsibility of deleting the memory is going to be on the caller, right? So let's actually do that, because then we can just skip this copy right here entirely in that resize. And then we can just simply say the out data is equal to this. And I think this will speed up our loading process, right? So let's just read it into the out data. And then let's also return a uint64 for out length. So we're going to do a character pointer reference out data and out length. And out length equals file length. Now over here, the data is shader data and shader length. We just pass in shader data and shader length. And now our code size is just the shader length right here. And then our actual code is, so the code actually expects it to be divisible by 4, right? The shader data has to be divisible by 4. That's why the code is actually an array of uint32s. So what we need to do is we need to take this data, but we need to do a reinterpret cast, right? We need to reinterpret it as a buffer of uint32 pointer, and do the shader data that way, right? So now we have code size. Do we need any flags? We do not need any flags. So we pass in the code and the code size. Now we can do vk create shader module. And then we need the VK device. And then the create info, shader create, allocator, we don't use that. And then the shader module. So VK shader module, new module. Okay, and then if this is not equal to VK success, then we have a problem. And we need to return false. And we need to say that failed to build Vulkan shader module for shader, which basically means we failed to create the microcode for this shader, right? But if it succeeds, now we can load it into the shaders map, right? So now this out shaders, we can insert using in place. And then we have the name of the shader, which is shader.name. And then we can put in this new shader module right here. Let's see how this works out. Unresolved symbol load shaders. Oh yeah, we changed the definition, so let's fix this up. And update our usage here. Graphics. Okay, so we get this, we load the data, and then we create our shader module. Boom. And the shader module was created. Do we get a validation error? No. And then it puts it into the shaders map, and then does the same thing for the fragment shader. And boom. Then returns true and success. So it looks like it loaded both of them with no error. Fantastic. So now our shaders are locked and loaded and ready to be inserted into pipelines. So let's go ahead and commit that. Load shader binaries, place them into shader map, and render context. Cool. So back to the pipelines. Okay. Create pipeline. So the first thing we need for this, like we were saying, is the stages, which is why we went on that big tangent just now. And I will be right back because I need to get a glass of water. All right, returned. Okay, so we need to fill out these shader stages right here with the stages, right? And so to create a pipeline, so we're gonna need some like way to abstract this. There's no way around it, right? We're not gonna want to fill all this out, but we're gonna need it, right? So most shaders that we care about are gonna be vertex and fragment, right? So let's start by creating like a pipeline info struct here, right? Which is gonna be our abstraction over creating a Vulkan pipeline. All right, so we're gonna take like a shader info. Actually, you know what? VK shader module, M vertex shader, and M fragment shader. That's what we're gonna do. So we're gonna take a module for the vertex and the fragment shader, and we're also gonna take in this pipeline info. We're gonna take a device in too. Pipeline info. Okay. So our stage count is going to be equal to 2. And then we're going to do shader stage create info. Okay, so we need 2 of these, right? We're going to do shader create infos, and there's 2 of these, right, for vertex fragment pipeline. Let's fill these out. So the 0 index 1 is going to have vert create. Yeah, I don't think we care about the flags. So we need the module. And then the name, I'm pretty sure that's just the entry point. Which is going to be main. I don't think we want a different entry point than main. Yeah, main is fine. Okay, and then we need stage. Yeah, and I think that's all we need for that. So that's a vert, and then we also need one for frag. And then we can initialize these. Unit 32. This is the standard size of the shader create infos. So it's include array. And then the stages themselves are going to be equal to shader create infos. Okay, so that filled that one out. Now we need the vertex input state. Vert input. Pipeline vertex input state create info. Okay. So the vert input. Flags. None. Okay. So this is essentially how we have, I think how we have multiple vertex streams potentially attached to a pipeline, because it's always possible you can have multiple. I think right now we only care about having one. Yeah. Oh, this is also how we do input attributes. Okay, input attributes and vertex bindings. Okay, so I see. Okay. So we need a separate one. So let's do this. Input binding. Input binding. Okay, so this is how we set up our actual vertex buffer stride, right? So the input rate is going to be equal to, you can either choose between vertex and instance, and since we're not doing any sort of fancy instance rendering right now, we're just going to leave this at vertex. The input rate, so this is essentially saying that the data in your vertex buffer, is it changing in frequency with the actual vertex or with the instance that you're rendering? Because there's certain techniques where, you know, you can sort of have the vertex data already stored on the GPU, but you can use the vertex buffer for like per instance data instead, right? So it's just a different use case there. And then the binding, this is just the index, that's 0. And then we also need the stride. So this one we actually do have to pass in, right? So let's have another struct for vertex info, or yeah, vertex state. So there's going to be uint64 and mstride, and then we're going to use this struct right here and vertex state, and then we're going to use that to fill this out. Input binding dot stride is going to equal pipeline info dot vert state dot stride. And then in this struct, we're going to say the binding count is going to be equal to 1, because we're only using one vertex buffer per pipeline for now. And the binding descriptions is just going to be a pointer to this. And because it's a pointer to this, this will actually go out of scope. So we're going to have to put this outside of these braces. So fortunately, because of that, we might as well just leave all of this out. All right. So now we have to fill out the other part of this, which is the vertex input state create, or vertex input attribute description, I meant. Which, this is where you describe each of your vertex attributes, okay? So we do need to pass these in. So let's say struct vertex attribute need a vector vk pipeline vertex input or vertex at vertex input attribute descriptions. Attribute descriptions. Let's include vector. And then this size is the same as pipeline info vertex state. And then we're going to basically copy this into this vertex attribute and see what we need. So we need binding. Or we can just infer the binding from the slot within the vector, which we probably will do. So remove binding. Location. Actually, yeah, remove binding, and then location, that's just going to be, that's going to be the index of it within the vector. So we really just need format and offset. Yeah. So m format and m offset. And then we just need a vector of these, and we're going to call them m attributes. And now what we can do is populate these vertex attributes. I should be using prefix for my for loops. Okay, and then attribute description. So the binding is going to equal 0, and that just refers to this input binding up here. I actually need to move this. All right, so that just refers to that binding. And then attribute description, the location, is we're just going to infer that from this vertex attribute right here. And we're going to cast that to a EN32, because there's no reason not to do that. This complicates the API. And then for the format, we're going to take this and extract it out of the thing. So we're going to take the vertex attribute reference attribute equals pipeline info vertex state attributes vert attribute. This will be const. And here we'll take the attribute format, and then we'll also take the attribute offset right here. All right, and now we can just plug that straight into this vertex input. So attribute descriptions is going to be equal to the data member here, and then the count. Attribute descriptions.size. And now we can fill out the graphics pipeline info dot vertex input state. Pointer. Just like that. And there we go. That's 2 down. Out of this long list of things. Now we need to do the input assembly state. This one's a little bit easier. Input assembly. So input assembly is basically like how our topology is working, right? So there's only a few things we have to fill out. So for example, topology. What kind of topology are you using? Are you using points, lines, triangle list, triangle strip, triangle fan? Right now we're only going to support triangle list, right? And that's your common topology. So we're going to leave it at that. And if we change it in the future, we'll of course allow different topologies. So And then primitive restart enable, this is like if you're using like triangle fan, you can actually embed a special signal to restart, or maybe it's triangle strip, but since we're not using that, we can just leave that as VK false. Yep. And that's it for that one. Next achievement unlocked. Now, moving on to tessellation state. Create info. Test state. Well, actually we don't care about this because we're not using tessellation state. Yeah, we're not using any of this. So this is just going to be left as null. Easy one. All right, viewport state create. Okay, so viewport state. This one, scissors and viewports. This is going to be dynamic. We don't care about this, right? Because this means you would have to embed like the width and height into your pipeline, which is silly, right? You shouldn't have to embed the size of your viewport into the pipeline. That's going to be fully dynamic. And the way we specify that is we have to tell Vulkan what things are we going to leave as dynamic. So I think we still have to fill this out. Structure type, viewport, state, create info. So we're going to give it the viewport state. But I believe later on is we're going to tell it to basically ignore that because we're going to provide that as dynamic information every frame. Yeah, 0 for the scissor count and 0 for the viewport count. Okay. Now we need the rasterization state create info. So for rasterization state, there's a lot of stuff we have to fill out here. So we need to specify cull mode. So this is going to be whether we're using, well actually let's start from up here. Flags, we don't care about those. Depth clamp, okay, so depth clamp, I need to look up what this one is, actually. Depth clamp controls whether to clamp the fragment's depth values as described in depth test. The pipeline is not created with depth clip state present, then enable depth clamp will also disable depth clipping primitives to the z-planes of the fruition as described in primitive clipping. Yeah, I don't think we want that. Clamp enable, we don't want that. Okay, and then rasterizer discard enable. Whether primitives are discarded immediately before the rasterization stage, that will be false. Okay, polygon mode. This one's pretty easy. This is if you wanted to like fill the polygons or use like lines, which would essentially be wireframe mode or points. So we want it to fill, so we're going with fill. And of course, when we support the other types of things, we will, you know, be able to pass that information in. Okay, and then cull mode, you know, this is your standard front face or back face culling. We're going to do front face culling. Because we're all about optimal. Yeah, front face culling. Okay, and then this is going to specify whether the front face is clockwise or counterclockwise, and I believe we want that to be clockwise. All right, and then depth bias enable, we do not want that. And then we can leave depth bias, these other things. Bias clamp, constant factor 0. This is good for shadow map rendering, actually. These depth biases. We might use those later on for that. Line width. Leave that at 0. And then clamp. All right, and that's our rasterization state. Now we need the multi-sample state. We're not using multi-sample, so this can be set to null. So we don't need that actually. Next is depth stencil state. So this is going to be like what kind of depth and stencil buffers we're using. So for now we're not using any of those, so we'll leave most of these disabled. Depth test enable is going to be false for now, although we will be turning that on whenever we get to 3D. Depth right. This is whether to write to the depth buffer. Depth compare, the comparison to use for depth testing. Usually that's less. And then depth bounds test enable. Made that false. And then this is where we can actually set up our min depth bounds and max depth bounds. Though this should be 0 and 1, because I think you have to enable something else if you want that to be something else. Now whether the stencil test is enabled, which we are not doing stencil buffer operations. And then stencil op state, this is how to run the stencil operations, which we are not doing. So those can also be left blank. Then we can pass this in. to our pipeline create info. And then we need to go to color blending. See how I'm talking about? This is a ton of state for the pipeline already. That is a lot of state right there. Okay, so for color blending, we will enable this eventually, but you do need to like sort of specify like the attachments for this. So logic up enable. Is going to be VK false. This allows you to specify logic operations for your color blending. And then the actual logic operation if you're doing that. We'll just leave it at VK logic copy, but this isn't going to do anything for us. And then we also need to specify the attachment count and then the attachments. So we'll just fill out one attachment for now since we're not using anything more than that. VK pipeline color blend attachment state. Color blend attachment. So we need to specify the color right mask. So this is all the colors that we're writing to. Color component R. We're going to do RGBA. But you can tell it if you only want to output to a subset. It's pretty cool. Okay, and then whether blending is enabled, which right now we are not doing blending, so that's VK false. And then the source color blend factor, which since we're not doing blending, these do not matter, but we will fill these out. Blend factor source. Blend factor, yeah, let's just leave this at blend factor 1. And then we also need it for source alpha and dest alpha. And then we need our color blend op, which we're going to leave as add. And the same thing for alpha blend op. And pass that attachment in. Now there's this other thing you can do called blend constants. You can pass in 4 of them, but we're not using these. Zero those out. Cool, and I think that's everything for color blend state. And we actually do need to fill out the multi-sampling, so that's a little bit of a correction. So Let's fill that out. That goes before depth stencil. VK multi-sample state create info. So sample, shading, enable, no, we don't want that. Then rasterization samples. This is going to be if you're using multi-sample, but we're not, so we're going to leave this at 1, count of 1. And then min sample shading. This is optional, we are not using it. And then sample mask. So we left it no pointer. And then alpha to coverage enable, we're not using that, but we will be for masked things, potentially. And then alpha to 1 is false. Okay, and then we can now pass that in. And now we can specify our dynamic states. And the two dynamic states we want right now are for the viewport and scissor. So the count is going to be the size of dynamic states. Okay. And then the dynamic states themselves, we're just going to pass in there. Then we pass in the dynamic state in there, and then cool. So those are the main structs that we need to fill out right there. Okay. Next thing we need to do is to create a pipeline layout. We also need the render pass. That this graphics pipeline is made for. Pass that in there. And the subpass, which is just going to be 0 for now. And then base pipeline handle is if you're using derivative pipelines, which we are not using. That could speed up the creation, and base pipeline index. Okay. Now we need to create our pipeline layout. Let's actually do that up. Well, yeah, let's do that up here. Create pipeline layout. VK pipeline layout create info. Layout create. So for push constants, we're not using those right now. So 0. Push constant ranges, null. And then we're not actually using any descriptor sets yet either, so I'm gonna leave that at null. And then if we're going to do check VK. VK create pipeline layout. Device layout create. And this create pipeline is going to do a VK pipeline out pipeline, and actually, pipeline layout will be separate. Create pipeline layout, yeah. VK pipeline layout, out layout. All right, see ya. Good night. All right, pipeline layout. We need to copy this. And put that layout right there. And this will return whether it's equal to VK success. And this needs a VK pipeline layout, M layout. Out pipeline, and then down here we can do the pipeline layout. Graphics pipeline layout is going to be equal to the info layout. And now we can finally create the graphics pipeline. Return VK create graphics pipeline. I'm not using a cache. 1, and this create info. Null allocator, and then the out pipeline. And return if that's equal to success. Boom. Okay. So now, in our create renderer context, we're going to create our pipeline. Create pipeline. Let's say create simple pipeline for now. Vortex create pipeline. You need to include that file first. First, we need to create the pipeline layout. Just the graphics device. We're going to put that in the renderer. Well, first we're going to have a shader data struct, right? Shader data, and it's going to be the combination of a VK pipeline layout, and it's going to have a pipeline. And then in our render context, there's going to be shader data for M simple shader. All right, I think I'm gonna end the stream for tonight.